your mind. Open your mind. Open your mind. Open your mind. Open your mind.
From the beginning of humanity until the 1970s, it was impossible to communicate secret messages without the risk of interception and decryption by eavesdroppers. The fundamental problem was the symmetric nature of encryption and decryption. Both the sender and receiver needed to use the same secret key, and somehow that key had to be sent from the sender to the receiver before any encoded messages could be transmitted. If an eavesdropper obtained sight of the key, they could then view and change the messages at will. By World War II, this had become a huge problem for armies, navies and air forces communicating via thousands of wireless radios. In October 1944, Walter Koenig at Bell Laboratories wrote the final report on Project C-43. Koenig suggested recipients of telephone messages could add interference to prevent eavesdropping, then subtract the noise from a recording to hear the messages in the clear. Although this was technically impractical at the time, it theoretically removed the need for a sender to pass a secret key to the recipient. 26 years later, in 1970, James Ellis, a leading British cryptographer, randomly discovered and read the final report on Project C-43. He then published a thought experiment on how to manage secret keys. The unthinkable was becoming possible, but still needed better mathematics to work for the recipient. In 1973, Clifford Cox, a Cambridge mathematician, joined the spy agency at Cheltenham. 6 weeks into his new job, a supervisor casually mentions Ellis's idea. Cox immediately realizes number theory was the answer. Multiplying two large primes is easy, even if they are more than 100 digits long. Factoring the two numbers from a much larger product is hard, very hard. It took the freshly recruited spy about 30 minutes to come up with this prime number solution. The young mathematician's discovery seemed immediately applicable to military communications, and it would become one of GCHQ's most prized secrets. Somewhat unfortunately for GCHQ, great minds think alike. Multiplying two large primes is easy for computers, even if they are more than 100 digits long. Factoring the numbers from the much larger product, i.e. working backwards from a semi-prime to discover the primes, is very hard. Using the two prime numbers as a private key held only by the recipient, a public key, otherwise known as the semi-prime product, could be passed to the sender to encrypt messages with an unbreakable cipher. If the public key was seen by an eavesdropper, they would still be unable to decrypt messages without the private key, which is the prime numbers held by the recipient and never transmitted. This is the basis of asymmetric cryptography. And in 1976, Whitfield Diffie and Martin Hellman of Stanford University and Ralph Merkle of UC Berkeley published a theoretical paper, New Directions in Cryptography. The following year, in 1977, Ron Rivest, A.D. Shamir and Leonard Edelman, three MIT academics, discovered an actual and elegant method for public key cryptosystems based on very large randomly chosen prime numbers over 100 digits long. The multiplications took seconds, factoring could take millions of years. The public encryption key would contain the product, the private decryption key would contain the two primes. It was safe to share the public key on an insecure channel because the factorization problem was so hard that it was, in effect, already encrypted, scrambled by a one-way function that was easy to perform but nearly impossible to reverse. This is the basis for asymmetric cryptography, as used by RSA, elliptic curve cryptography, secure socket shell, and transport layer security, among others. Asymmetric cryptography is applied throughout the world in millions of systems now. even those that drop down to simpler, symmetric cryptography after keys have been securely transmitted using asymmetric cryptography. So there we have it. The final report on Project C43 was gathering dust for about 30 years before it became the foundation stone to the biggest change in cryptography in thousands of years. Let's hope something we write might do that one day. But for now, this is all. Thank you very much for listening.